My name is John Schull. I'm a graduate student here at Oldham University, and I'm doing a semester project in transportation and logistics. And my transportation was picked to do a YouTube video demonstrating the branch and bound method. Computer program that I've used, software called NetLogo. Alright, so the problem in question is a maximization problem. We have 3 variables, 4 constraints. The 4th constraint, as you can see, is the 3 variables have to be greater than or equal to 0 and also have to come from the integer population set. Variable 1 weighs up to 3 pounds, variable 2 weighs up to 2 pounds, variable 3 weighs up to 1 pound. So what is variable 1? x1 is a chicken. x2 is trail mix. And x3 is alcohol, aka beer. Again, first constraint is that we can only hold up to 50 pounds. Second constraint is that these items take up an area or a mass. And so we have a variable of 10. Chicken takes up 1 unit of this measurement. Your trail mix, which is light, small, only takes up a quarter of this mix. And your beer takes up half. Alright, so like I said, 1 is weight, 2 is area, and 3 is the fun one. So 3 is basically a 3 is a satisfaction constraint. So basically our satisfaction constraint is on this given day our maximization problem, which is an energy problem. We need this much energy to hike our trail, hence why we have a knapsack and we're trying to pack certain items. So we don't know how many of items what to pack. So constraint number 3 goes after the fact that even though we are hiking and even though this is a physical exertion, we still want to have fun. So as you can see, you get 3 satisfaction points if you bring 1 chicken. Trail mix, I don't know about you guys, some trail mix is pretty good, some trail mix is horrible. So in this case you only get a quarter of a satisfaction. And for our 3rd constraint, beer, as Dr. Newing likes to bring up a lot, you get a satisfaction of 10. But just one thing to take in mind is that in terms of energy, it is a negative 8.6, so that's just something to keep in mind. So again, constraint 3 is a satisfaction. What you will see is actually a NetLogo representation. So first thing, we're going to end up with x1 equal to 4.699, x2 equal to 16.867, x3 equal to 2.167, and our function, which we'll say z, has a total energy of 118.265. Now, this, as we said, this is with an integer relaxed. So this is important because what this actually identifies is the upper bound for your entire problem. So later down the road, as we start to get into the integer constraint, you'll never be able to do better than this. So again, the overall you'll ever be able to max out of this equation is 118.265. So next question is there a lower bound? Yes, there is. And the best, the way to do that is basically take all of your variables. So x1 becomes 4, x2 becomes 16, x3 becomes 2. Plug this back in the original equation. And I believe we get 109.2. Yes. All right, so 109.2 is our ultimate lower bound. And 118.265 is our ultimate upper bound. And I'm going to start the process of the branch and bound. Now, to give you a heads up, this is actually a pretty lengthy branch and bound problem. I'll spend more time up front on the initial few steps. I'll accelerate through demonstrating with the program so you have an understanding of visual animation of it. So our initial starting point is going to be exactly what we had from our original linear programming problem with the integer variable, with the integer constraint relaxed. So we'll call this node 1. Node 1, as we said, has a value of 118.265 with x1 equal to 4.699, x2 equal to 16.867, x3 is equal to 2.167. Alright, so what we need to do now is we're going to basically isolate one of the variables and, quote, branch off of it. How do you isolate the variable? Well, basically it's a simple rule. You look at the decimal points, and in this case, because it's a maximization problem, we want to find the largest decimal point, which is actually the x2 variable. The x2 variable's decimal point is 0.867. So we're going to branch off of x2. x2, it is right now 16.867. The whole idea is we don't want that number to happen or occur. So in branching, the two options we're going to put in is basically x2 is less than or equal to 16, and x2 is greater than or equal to 17. This variable to be anything less than 16 and anything greater than 17, inclusive. So as you can see, pretty straightforward. You're going to follow this approach for every branch on the way down throughout the system. So it's a really straightforward, easy approach to do. So as I said, in this case, we're going to go with x2. And the subsets, so we'll have x2 is less than or equal to 16, and x2 is greater than or equal to 17. So given these two subsets, we now have two new nodes. Node 2, node 3. So basically what we're going to do is we're going to go to node 2 first, just because, no particular reason. You could go to node 3 if you'd like. I decided to go to node 2 because I like to work left to right. All right, so at node 2, we're basically going to resolve the linear programming problem, but now we're going to add in this new constraint, and the constraint of x2 less than or equal to 16. So given all the original constraints, putting this back into the original equation as a new constraint, we end up with the following optimization. All right, before we do anything with that, we now need to go over to our other one at x2 is greater than 17. Same thing. We're going to put in all the original constraints, and now this one. We're not going to put in the x2 is less than 16. We're not going to put in the x2 is less than 16. So putting this back in, we end up with an optimal solution over here of 118.1019. x1 is equal to 4.602. x2 is equal to 17. x3 is equal to 2.194. Alright, so now we have to pick one. Being that it's a maximization problem, we're going to pick the one that gives us the best answer, which is node 3. So this value is important because from here on down, as we branch further down node 3, this is our new upper bound. We'll never be able to have a solution better than this. As you can see, our original solution without the integer constraint was a little bit better than this. So basically that's how the process works in a maximization formula. As you go through down it, you're going to end up getting those smaller results, but usually depending on different sizes. So now we're basically doing the same process over again that we did with node 1, except now we're just looking at node 3. So x2 is an integer. Since it's an integer, we leave it alone. So we're only looking at x1 and x3. x1 has the greatest decimal point, so we're going to go off of x1. Alright, so if x1 is at 4.601, we want to go not include that, so we're going to go outside of it. So we're going to have x1 is less than or equal to 4, x1 is greater than or equal to 5. Alright, now this time when we go back through just like we did the previous problem, we have to use our original constraint problems, original constraint equations. We also have to use its parent node, which is node 3's constraint. So originally we had 4 of the constraints. Fourth one was the integer constraint, which we relaxed, so really we only have 3. We then have the constraint off to node 3, which would be x2 is greater than or equal to 17. And then we have the new one that we're testing, which is going to be the x1 must be less than or equal to 4. So we have 5 constraints we're putting back in. We would then resolve the equation again. And we'll have 2 new nodes. So for this one in particular, we're looking at, and we'll call it node 4. And the other one is node 5. So for node 4, we end up with an optimal solution of 117.0886. x1 is equal to 4. x2 is equal to 17.823. x3 is equal to 2.354. Alright, so now, as before, we go to node 5. Alright, so same thing as before. We have to put its parent constraint in. x2 is greater than or equal to 17. Also have our new constraint, x1 is greater than or equal to 5. We put that in. We end up actually getting a non-feasible solution. Basically, given those constraints, we can no longer solve that linear programming problem. So what ends up happening at node 5 is basically, we'll call it a cut, a clip. You get rid of it, you throw it out. We don't get any beer, we don't want it. No satisfaction, so node 5 is actually done. So on this point from here on, we'll have no other branches or bounds off of node 5. All right, so going back to our two nodes that we do have available, is node 4 and node 2. So how do we decide which one? Again, we go after what's going to maximize our energy for the day, so it's going to be node 4. So, again, repeating the process, we look at node 4. All right, so at node 4, we're dealing with, we have one integer variable, it's x1, so we're not going to deal with that. We have x2 and x3. X2 has the largest decimal, so we're going to go off of x2. And the value is 17.823, so we're looking for less than 17 on one, and x2 is greater than or equal to 18 on the other. We will call these node 6 and node 7. All right, so again, going left to right, start with node 6 now. So this time around, just as what we did with node 4, we have to follow up the chain. So think of it as a tree going up the branches. So basically, we have to make sure that we do this constraint, which would be the connection between node 6 and 4, constraint connection between node 4 and 3, and 3 and 1, plus our 3 original constraints. So in theory, we have 6 constraints right now to solve our problem. And we're going to get up with a solution of 111.975, x2 equal to 17, two integer variables. x3 is going to be equal to 2.375. So again, we have not hit all integer variables, so we will have to continue on. Obviously, we still need to do 7, so I apologize, got ahead of myself. All right, so now on to node 7. Same thing, except we follow up the line of chain of commands here. So we're going to do the link between 7 and 4, 4 and 3, and 3 and 1, plus our original constraints. And we're going to end up with a optimization value of 116.8704 with x1 equal to 3.870, x2 equal to 18, x3 equal to 2.389. All right, so at this point, we have 3 nodes to consider. We have node 2, node 6, and node 7. Again, highest number wins. Looks like it's going to be node 7. All right, so we start at node 7, and we begin to branch off. All right, so again, we have one integer variable at x2, so we'll leave that alone. We're going to then look at x1 and x3. The largest decimal wins, so it's going to be x1. x1's current value is 3.87. We want to find something outside of that region. So we're going to 2 new nodes, we can call them 8 and 9. And we want to look for x1 is less than or equal to 3, and x1 is greater than or equal to 4. All right, so we'll start with node 8. We get a solution of 115.4051 with x1 equal to 3, x2 equal to 19.190, and x3 equal to 2.620. All right, swing over to node 9. All right, so as before, I'll state it again. We're going to do all of the links in chain in command. So 9 to 7, 7 to 4, 4 to 3, 3 to 1, and our previous 3 constraints. So we have a total of 7 constraints on this one. And for actual node 9, we end up with a non-feasible solution. All right. Now we have 3 variables to pick from. Again, we want to maximize. So we have node 8, which is 115.4051, and node 2, which is 115.34. Node 6 comes in at 111. So we're going to go with node 8, 2, which will go off to 1 down the line. So as you can see, we have a couple options here. We said we're going to go with node 8 because it had the highest maximum, which it does, of the available nodes it can be looked into. So we're going to branch off 8. We have 11, node 10. Okay, so for, what do we got lost here? Hold on. Okay, so at node 8, x1 integer, so we're not messing with that. We're looking at x2 and x3. x3 has the largest decimal, so we're going to go ahead and use x3. x3's current value is 2.670, so we want a value less than that, so x3 less than or equal to 2, and we want a value greater than that, so x3 greater than or equal to 3. Alright, so we go ahead and solve our equation, and we get back a nice non-feasible answer, given the numerous constraints ahead of it. Doesn't surprise me. So 10 is done, which is good, because we want to try to rule out as many of these as we can. Alright, so let's look at node 11. Node 11, x3 is greater than 3, given all the previous constraints. We do have a solution. 10 was a non-feasible solution. Node 11, we have a maximum value of 113. So right now we have the options between node 11, node 6, and node 2. In this particular case, node 2 actually has the best choice. So we're now going to switch over to the left side and go off of node 2. Node 2's current solution, x2 is an integer at 16, so we're not going to look at that. We're going to look at x1 and x3. Alright, so looking at 2, we're going to look at x1 because the has the largest decimal at 0.941. So x1's value was 4.941. We want it to be less than or equal to 4, and we want it to be greater than or equal to 5. 12 and 13. Alright, so we're going to go left to right, solving for 12. And we're going to get a value of 105.76. At this point, we have 4 nodes to look at, 12, 13, 6, and 11. Again, we want the maximum. 13 is 114. Beat that. No, that looks like the node is 13, so we're going to go off of node 13. Call these 14 and 15. Alright, so x1 is an integer, we're good. x2 has the largest decimal, we're going to go after x2. So x2 currently is 15.789. So we want x2 less than 15, and we want it greater than or equal to 16. Put it in constraints. For node 14, we get 111.971 and the given variables. So x2 currently is 15.789. So we want x2 less than 15, and we want it greater than or equal to 16. Put it in constraints. For node 14, we get 111.971 and the given variables. So for node 15, given the constraints ahead of it and the information off of the new x2 being greater than or equal to 16, we end up with a non-feasible solution. So just again to remind you, the non-feasible solutions are because for whatever reason we are unable to meet all of the constraints. More than likely they're the constraints that have been added on have compiled up to a point where it's no longer feasible to solve the problem. Which is good because it's less work for us and more beer drinking for the rest of us. Alright, so from here now we have a couple choices, 12, 14, 6, and 11. Looking at the values, looks like node 11 has the highest value at 113, so we'll go to node 11. Alrighty, so our 2 next sequent nodes are 16 and 17. Alright, so at node 11, x3 is an integer, x2 and x1 are our variables to look at. x1 has the largest decimal, so we're going to go look at x1. x1 is currently 1.571, So we want x1 less than or equal to 1, and we want x1 greater than or equal to 2. In solving for node 16, we end up with a value of 112.038 and the given variables. For node 17, follow up the line of the chain of command, make sure we have all our constraints, and we get a value of 112.4 with the given variables. So now, which node we pick? 17, 16, 6, 12, or 14. We have 5 options. The highest one, let's see here, to be 112.4. So node 17. So from node 17, we're going to go into 2 more, 18 and 19. Yeah, so we do. So node 17, we're getting some results that are nice. So we have 2 integer variables, which is nice because that makes the decision for us very easy. We've ruled out variable x1, variable x3, so we're only focusing on variable x2. And this is going to be for node 18 and node 19. So x2 is 20.5, so we want something less than or equal to 20. And we want something greater than or equal to 21. So at node 18, given that constraint, we end up with a value of 111.933. I'll explain why the decimals sometimes are important. We have x1, x2, and x3 again with 2 nice integers. So we have to solve for node 19. Given all the constraints, and our new constraint of x2 has to be greater than or equal to 21. Node 19 actually favorite type of node. Get out of here, buddy. We don't want you in here. Alright, so now, we still have a bunch of options though. So what do we pick? We have 6, 12, 14, 16, 18. We have a total of 5 again. Again, we're going for the highest. So let's see here. Looks like it's going to be node 16, just by a little bit. It's 112.038, that's correct. Alright, so off of node 16, I'm going to draw this over here a little bit, a little screwy. Alright, so we're going to use node 20 and node 21. Given the fact that 16, we did have one integer, and that was our x1, so we're looking at x2 and x3. x2 had the largest decimal, so we're looking to do that. So x2 needs to be less than or equal to 21, given that its original value was 21.94, and x2 needs to be greater than or equal to 22. Alright, so at node 20, we end up with a value of 106.295. Node 21, with the given constraint, we end up with a 0.944 for x1, 22 for x2, a nice integer, and 3.167 for x3 with an overall score of 111.944. As I mentioned earlier, the decimals are important. 111.933 node 18 is just under node 21 at 111.944. So now that we are here, we need to decide which one of the 1, 2, 3, 4, 5, 6 nodes we're going to go after. Looks like node 6 actually has the highest. It does. Node 6, 111.975. It's a battle of inches. Alright, so at node 6, we have 2 nodes are coming off. We call them 22 and 23. Node 22, well, actually we've got to figure out what variable here. So x2 and x1 were both integers, so that's nice. So all we're looking at is x3. x3 is currently 2.375, which means we need x2 to be less than or equal to 2, and we need x2 to be greater than or equal to 3. Solving with all the new constraints, our node 22 comes about to be dead, i.e. can't solve it. We're done with node 22. So let's look at node 23. Node 23, we do get an answer, and it is 106.6. And guess what? x1 is an integer, at 4, x2 is an integer at 17, and x3 is an integer at 3. Holy cow. That's great because that is our first actual possible integer solution. So again, node 23 is all integers, and big circle around it. Which means that at this point, unfortunately, we're not done because we still have some other nodes to examine, and we still need to figure out if that's maybe the best choice. It still might, that doesn't necessarily guarantee it's going to be the best choice. It is an integer solution, but it doesn't necessarily mean that it is, again, the maximum integer solution. So we have node 23, node 20, node 21, node 18, that's 4, node 12, node 14. So we again have 6 nodes. And at this particular case, so actually we're going to go to node 14, back off to the left side. Alright, so at node 14, 2 more nodes. Just when we thought we were done, we're not done. We keep on going because this is the problem that never ends. So we have node 24, node 25. Alright, so we're looking at the x1 variable. So we have x1 is going to be less than or equal to 5, x1 is going to be greater than or equal to 6. So at node 24 we have a solution of 109.725. And at node 6 we have a solution of, I'm sorry, not node 6, and at node 25 we have a solution of 102.568. So let's see here, we have 3, 4, 5, 6, 7 possible nodes, one of which is actually done with the integer. Looks like to be node 21 by a hair. So we're going to do node 26 and node 27. Alright. Well, at node 21, we had one integer variable, but not between x1 and x3. X1 has the largest, so basically we're going to try to force here, x1 is going to basically be forced into being less than or equal to 0, which will be 0 because of our original constraint, which is good to know. And our variable over here for x1 will be greater than or equal to 2. So we know we go into 26. 26 ends up with a solution of 110.354. Node 27 ends up with a solution that is infeasible. I'm sorry, not greater than or equal to 2, greater than or equal to 1. So the constraint between node 21 and node 27 is x is greater than or equal to 1. It's an error on my part. So now node 27, like I said, is infeasible, which means it's dead. Again, one of our favorite variables. All right, so we're still going here. So let's go over to node 18. Node 18 is going to have our highest value, which is right next to us, and that is at 111.933. So from node 18, we originally did have 2 integer variables. Let's see if this turns into something here. So node 18, we're going to break off into node 28 and node 29. Okay, so at node 28, we end up with a value of 109.4, and at node 29 we end up with a value of 111. At node 28 we have 3 integers. That's awesome. So x1 equals to 2, x2 equals to 20, and x3 equals to 3. We're gonna big circle this guy. So node 28 is added to our possible integer solutions, and if you actually look, so node 28 is added to our possible integer solutions, and if you actually look, you can basically tell that node 23 and node 28, like I said, integer solutions, but node 28 has a higher maximization, so you can almost pretty much rule out node 23 if you wanted to at this point. So let's look at 29. I had a value of 111. Well, at 29, we end up with 3 integers. Look at that. x1 equals to 3. x2 equals to 19, and x3 equals to 3. All right. So kind of the same situation with node 28 and node 6. I'm sorry, node 23. 29 actually has a higher value than 28, so we can basically kind of put a little x here next to 28, letting us know that we're not going to use that one either. So now here's the fun part. As stated before, I said it was important to keep aware of the upper bounds and lower bounds. So if you look at the nodes that are left, node 12 is 105.76. That means no matter what we do from node 12, we'll never do better than. So as I said earlier, when we looked at the upper bounds, given the way that the branching works, when you look at node 12, it has a value of 105.76. No matter what craziness we come up with on the left side, we'll never be able to do better than that value. So what we can do is we can basically kind of cap this off, where we're done with this area. The reason why we're done with that is because our current solution is 111. So does that work out for other options? Well, node 24 does. Node 24 maxes out at 109.725, so that's pretty much done. Node 25, 102.568. Come on, get out of here. That's way over. So in theory, this whole side is done. So this side of the equation is done. So we still have some other nodes left. So hopefully we can get rid of them. We have node 20 and node 26. Well, 20 maxes out at 106.25, so that's done. Cap out 20. And 26, what is 26? 26 is 110.354, it's done. All right, so all possible, we have not fully fulfilled every possible solution, but we don't need to because of the nice ability to know that we'll never do any better than the upper bounds. So at this point, this solution is done. So what is our solution? All right, so our path is node 1 to node 3 to node 4 to node 7 to node 8 to node 11 to node 17 to node 18 and finally to node 29 where we get our integer solution. This means we have all these additional constraints we have to consider, so let's get them all out. So if you look at these, we can actually start to eliminate some. So right here, x2 has to be greater than 18, outdoes 17, so we can kind of get rid of that. We don't need to restate those double constraints. We have right here x2 is less than or equal to 20, so we do need to keep that one and that one for x2. So let's look at x1. x1 has to be less than 4, x1 has to be less than 3, well 3 outdoes 4. x1 has to be greater than 2, x1 has to be greater than or equal to 3. Well right there, that tells us that x1 has to be 3. So we can actually rewrite that constraint if we wanted to say x1 equals 3, or whatever. And for the cases of x3, we only have 1, and x3 has to be greater than or equal to 3. All right, so as I stated, for the final conclusion of our maximization problem, in order to have the most amount of energy, given that we have 3 choices of things to pack, chickens, and when I mean chicken, I mean like a whole chicken, not like chicken breasts or grilled chicken or Wendy's chicken fried sandwiches. I mean like a whole chicken, hence why it takes up a little bit of room, basically 1 cubic foot per chicken. Unfortunately, it's shoved in your knapsack. I'm not really too, please don't, if you're from PETA, I'm sorry. X2, which is our trail mix, we get a good amount of energy from that, almost as much as the chicken, except, it's lighter, it's smaller, so it doesn't take up that much weight, and in terms of area, it doesn't take up anything. So, again, our third variable, beer, alcohol, liquor, whatever you enjoy, you got to have some fun here. You're not only hiking, but you're enjoying the wilderness. I don't know, maybe you're hiking with your friends, maybe you're hiking with your wife, maybe if you're Dr. Newing, you're hiking away from your wife. I don't know what to tell you. So, again, the 3 variables, x1, chicken, x2, trail mix, x3, beer. All right, so our original constraints still hold the true. So 3x1 plus 2x2 plus x3 must be less than or equal to 50, so we can only carry 50 pounds. Each chicken weighs approximately 3 pounds, some big chickens. Each trail mix pouch weighs about 2 pounds, and each alcohol bottle that you bring weighs about 1 pound, so you can think of it as 16 ounces. For the second constraint, which we considered like our area that our knapsack can hold, the chicken takes up 1 cubic foot. The trail mix, being that it is trail mix, only takes up 1/4 cubic foot, and the beer takes up about 1/2 cubic foot. So that has to be less than or equal to 10 cubic feet. We can't outpack our pack. And then the last one, which is our general enjoyment, satisfaction of the day, requires us to then, for a chicken, we get some satisfaction out of that. We get 3. Not as high as you might think because, unfortunately, like I said earlier, it is a whole chicken. It takes a lot of work to get to your goal.
For the second part, for the second variable, trail mix, as I stated earlier, we don't, I don't know about you guys, there's some fantastic trail mix out there. And then there's a trail mix that just literally tastes like you're eating dirt. So this must be the trail mix that's, well, maybe it's not dirt because you still get positive enjoyment out of it, but you're only getting 0.25. And then, of course, last but not least, our alcohol, which gives you the most enjoyment with a value of 10. So, and again, that has to be greater than or equal to 40. The new constraints we derive from solving the branch and bound for the variable x1, which is our chickens, we basically have to bring 3 chickens. No questions asked, we're bringing 3 chickens. We're not bringing 2, we're not bringing 4, we're bringing 3 chickens. For variable 2, for our trail mix, we have to have at least 18 packs, but we can't have any more than 20. Once we go over 20, it's too much. Like I said, it's just too much. We're not even going to go down that road. So for the last variable, x3, the fun one, the alcohol, to be honest, everybody's been waiting for that one. I know I've been too. It has to be at least greater than or equal to 3. So we have to have 3 beverages. I don't know, maybe one to get you going, one while you're hiking, and one while you're taking a break, or one while you're done. It kind of makes sense to me. So our final solution is that we are going to bring 3 chickens because we have to, because that's what our solution tells us to. For our trail mix, we're bringing the house, we're bringing 19 of it because you know why? We couldn't make up our mind. We didn't want to bring 18 because we had to be more than 18. We didn't want to bring 20, so we said, you know what, we'll go right in the nice happy middle there with 19. And the last variable, x3, our alcohol, we will bring 3 of that as well. And that gives us a total amount of energy of a nice round 111. And that concludes this. I hope you enjoy the NetLogo version of this. There's a lot more other things you can do on the animated side of NetLogo. And if you guys ever have any questions about it, feel free to email me. It's jshull, 1L, so it's JSHUL 003 at odu.edu. Other than that, the class was a lot of fun. I think I learned something, and I hope this makes branch and bound seem a little bit more interesting. So.